Welcome to Yatimkhana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Today we are going to study the topic which is called as need of modulation and demodulation. So our today's topic is need of modulation and demodulation, and on this topic only we are going to focus today. Now, in day-to-day life, we know that we are using so many electronic devices such as mobile, television, radio, computer, along with internet connection. Because nowadays, if you have a laptop or if you have a computer and if there is no internet connection, it is a dead instrument. So, in this way, in day-to-day life, we are going to use these electronic instruments for the purpose of communication. For the purpose of communication. And in communication, we know that antenna plays a very important role. Antenna plays a very important role. So antenna is what? Antenna is an electronic device, you can say that, which converts an electrical signal into electromagnetic waves, or vice versa. Or vice versa means electromagnetic waves into electrical signal. So here we know that in communication, an antenna is used to convert the information signal, that is electrical signal, into electromagnetic waves and vice versa. And these electromagnetic waves, which is nothing but our information signal, are transmitted from source to destination in free space, are transmitted from source to destination in free space, that is your air, almost with the speed of light. Almost with the speed of light. So this is our general introduction, and now we'll proceed how to transmit or how to pass the information from source to destination. So to pass the information from source to destination, one thing is very clear, that you want an antenna. For what purpose you want antenna? To convert your electrical signal, that is information signal, into an electromagnetic waves, which is also called as EM waves. So what is EM wave? So there is a electric field. So all of you know the sine wave. Sine wave is nothing but the best example of electric field, where electric field is varying sometime in positive half cycle, sometime in negative half cycle, and this is the electrical field. Electric field, so red, you can see that, and this arrow is shown because that is the instantaneous value of voltage with respect to time. So sometime voltage is in positive half cycle, sometime voltage is in negative half cycle, like that. So this is a electric signal. So electromagnetic waves are having electrical signal varying with respect to time, as well as magnetic signal varying with respect to time, and both are perpendicular to each other. That is the property of electromagnetic wave. Now you can see here a blue. So this blue is nothing but your magnetic field, and that magnetic field is also varying continuously with respect to time. That magnetic field is also varying continuously with respect to time, and in this way this magnetic field is perpendicular to the electric field. And lambda, you know very well, lambda is the distance between two adjacent positive peak of the sine wave. So this is one of the diagram with which you can understand that the electric field and magnetic fields are perpendicular to each other, and they are propagating in free space almost with the speed of light. Now this is important. For effective transmission, that is radiation, you want to transmit your information signal from one location to another location. For efficient or effective, for efficient transmission, transmission is also called as radiation of electromagnetic waves. These electromagnetic waves is nothing but your information signal converted into electromagnetic waves. The relation between The frequency of an electromagnetic wave, the relation between the frequency of an electromagnetic wave, that is information signal, and size of antenna. Size means length of antenna, and length of antenna which is used to transmit or receive the signal as a transmitter or receiver, is given as the size, that is the length of antenna, must be equal to the wavelength of electromagnetic waves, that is information signal. So there is a relationship between the size of antenna, that is the length of antenna, and wavelength and wavelength of an information signal which is converted into electromagnetic waves. So in this way, what is that relation? The relation is like that: for efficient transmission, this is important, for efficient transmission, the size of antenna must be equal to the wavelength, of that electromagnetic waves. And this is a problem. And this is a problem. So we'll just try to understand that now. What is the relationship between size of antenna, that is the length of antenna, and the wavelength of an information signal, and that is the electromagnetic waves. So what is that relation? The size of antenna must be equal to the wavelength of electromagnetic waves, that is information signal. So this is the relationship between size, that is the length of antenna, and wavelength. Okay. Now let us proceed. So this is called your efficient transmission or effective transmission. So here transmitting antenna, this is a tower. On this tower there is antenna. So this is a transmitting antenna and this is a receiving antenna. So electromagnetic waves, see here, electric field and magnetic field. Electric field is shown in the red line and magnetic field is shown in blue lines. Okay, so both are perpendicular to each other. So electric field and magnetic field, as I already shown you in the first slide, red line is your electric field and blue lines are the magnetic fields. So here also that is there. So in this way, the information is transmitted from transmitter to the receiver with the help of electromagnetic waves. And just 1 minute before, we have discussed efficient transmission is possible. Efficient transmission, that is the radiation, is possible if the size of the antenna is equal to the wavelength of electromagnetic waves. Now one more example of electromagnetic wave is here. So signal green signal is nothing but your electric field. See here, green signal is nothing but electric field which is varying with respect to time, and these arrows are shown instantaneous value of voltages of that signal with respect to time. Here violet signal is a horizontal, and that is nothing but magnetic field. So electric field and magnetic fields are perpendicular to each other, and here we are interested in the wavelength. What is the wavelength? Wavelength is the distance between two adjacent positive peak of electric field, and this wavelength is there. Now just we have discussed that the size of antenna for efficient transmission or effective transmission, the size of antenna must be equal to the wavelength of that information signal or electromagnetic waves. So this is the wavelength. Now in electronics, lambda is nothing but wavelength, and crust means the distance between two adjacent crust, and electronics we call positive peak. In electronics we call positive peak is the lambda, and this lambda is nothing but time t. This lambda is nothing but time t. So this you just remember and then we'll proceed. So here lambda is equal to time t, and you know frequency f is equal to 1 by t. So there is an inverse relation between frequency and lambda. Now we'll proceed to understand what is the size of an antenna for a particular information signal or an electromagnetic waves by taking one example. Now here see, but all information signals are basically low frequency signal. Information signal is what? A low frequency signal, and wavelength lambda for the low frequency signal is in kilometer. Therefore, the size, that is the length of antenna, must be in kilometer. Therefore, the size or the length of antenna must be in kilometer. So, our problem is what? Our problem is the length or the size of the antenna must be equal to the wavelength of information signal, that is electromagnetic waves, and 99% or 100% the information signal is always a low frequency signal. So in our first lecture we have seen the voice frequency of the human being is a low frequency signal, 300 hertz to 3000 hertz. Blood pressure is again a low frequency signal, and so many information signals are always low frequency signal, and there is an inverse relation between frequency and lambda. There is a inverse relation between frequency and lambda. That equation will come to know in the next slide only. Inverse relation between frequency and lambda means if the frequency is low, wavelength lambda is very large. If the frequency is low, wavelength lambda is very large. So large means what? The wavelength is always expressed in meter and kilometer. Lambda is what? Always given in meter and kilometer. So for a low frequency signal, the lambda is in kilometer. The lambda is in kilometer. So here that is what explained. But all information signals are basically low frequency signal, and wavelength, that is the lambda for low frequency signal, is in kilometer. Therefore, the size of the antenna must be in kilometer, which is not affordable or possible. For example, now we have taken, for example, if the electromagnetic waves, that is information signal, is of frequency f is equal to 100 kilohertz. Let us consider a low frequency signal of 100 kilohertz. And let us try to calculate its wavelength, because size of antenna is equal to wavelength. Because size of antenna is equal to wavelength. So let us calculate the wavelength for a information signal or electromagnetic waves of f is equal to 100 kilohertz. So here the relationship between frequency and lambda is given by equation f is equal to c divided by lambda. F is equal to c divided by lambda, where f is equal to frequency, which we have taken 100 kilohertz. C is equal to speed of light in vacuum. Speed of light in vacuum, and it is something 299,792 kilometers per second. But normally in our practical calculation we take it 3 into 10 raised to 8 meter per second. 3 into 10 raised to 8 meter per second we take it. So that you just remember the speed of the light, and lambda is the wavelength, and lambda is the wavelength. So this is the equation which represents the relationship between frequency and lambda. C comes into the picture. The c is the velocity of light. Sometimes it is given as c is equal to f into lambda. C is equal to f into lambda, simple multiplication. Or sometimes this equation is stated, instead of frequency f, it is denoted by the symbol mu. Mu is the frequency. C is equal to mu lambda. So various reference books or textbooks are using various symbol for frequency. So here we'll standard use f is equal to c upon lambda, where c is equal to 3 into 10 raised to 8 meter per second. We'll take it. And now we'll calculate the lambda for a what? 100 kilohertz information signal. Our information signal will consider 100 kilohertz, and we'll calculate the lambda, and we'll try to understand what should be the size of the antenna. What should be the size of antenna? So now where c is equal to 3 into 10 raised to 8 meter per second, therefore lambda is equal to c divided by f. Our lambda is nothing but, therefore lambda is equal to, comes to what? 3 into 10 raised to 8 meter per second divided by 10 into 10 raised to plus 3 hertz. So this calculation is 100 kilohertz. So 100 kilohertz will become 100 into 10 raised to plus 3 hertz. So here 1 divided by second is hertz. 1 by second is hertz. So this hertz will get cancelled. Therefore lambda is equal to 3 into 10 raised to 8 meter second, 1 by second, and this hertz is cancelled. Lambda is equal to 3 into 10 raised to 8 meter, and this 100 into 3, 10 raised to 3 means 10 raised to 5 will become 10 raised to minus 5, will become 10 raised to minus 5. And in this way you'll come to know that the lambda is equal to 3 into 10 raised to plus 3 meter. 3 into 10 raised to plus 3 meter, that is lambda is equal to how much? 3 kilometer. That is lambda is equal to 3 kilometer. So can you imagine the size of antenna required to transmit the signal of 100 kilohertz is 3 kilometer, and it is practically not affordable. And it is practically not affordable. In this way, the size of antenna is 3 kilometer for electromagnetic waves, that is information signal of 100 kilohertz, and it is very long. And it is very long. So what is the solution then? Most of the time, an information signal is in kilohertz only. Most of the time, an information signal is in kilohertz only. Therefore, the size of an antenna is further increases. We have considered 100 kilohertz. We have considered 100 kilohertz, and most of the time it is in kilohertz, less than 100. Then the size of antenna will further increase because the wavelength lambda the wavelength lambda of low frequency signal is very large. Inverse relation between the wavelength lambda and frequency. Lower the frequency, higher the lambda. So in this way here, let us take the example now. For example, the frequency of human speech. The frequency of human speech, that is called voice frequency. That is called voice frequency is 300 hertz to 3000 hertz. 300 hertz to 3000 hertz. I am talking about voice frequency, not audio frequency. Audio frequency is 20 hertz to 20 kilohertz. That is different. Voice frequency. So voice frequency is 300 hertz to 3000 hertz. That is the bandwidth of human speech. Is what bandwidth is nothing but f2 minus f1, higher side divided by higher side minus lower side. So bandwidth comes to 2700 hertz, means 2.7 kilohertz. So this is the actual bandwidth required. This is the actual bandwidth required for the human speech, But in communication, the bandwidth allotted. But in communication, the bandwidth allotted for human speech is 4 kilohertz to avoid the interference. Now let us consider to transmit this signal. To transmit this signal, the size of antenna will be how much? It is a 4 kilohertz only, this signal. The bandwidth of this signal is 4 kilohertz. We have considered the signal of 100 kilohertz for which we got the answer what? The band for which we got the answer lambda is equal to 3 kilometer, and that is the size of antenna. Now you can imagine for a signal of 4 kilohertz, the size of antenna is very large than 3 kilometer. Is very large than 3 kilometer. So here the relationship is given here. So here you can see the wavelength lambda. Okay, so this is the wavelength lambda, distance between two adjacent crusts, you can say, or distance between two adjacent positive peaks. So here this is also the time. So time is large, and there is an inverse relation between frequency and time. When time is large, frequency is low. When time is large, frequency is low. So here this time is very large, means this signal is the low frequency signal. And when this is a low frequency signal, the wavelength lambda is large. The wavelength lambda is large. So there is inverse relation between frequency and lambda. Now as you go on increasing the frequency, see here, the time is decreased. So time between two adjacent crust, or time between two adjacent positive peak is less. And when the time is less, the frequency is high. And when the frequency is high, you see the lambda. Lambda is the distance between two positive peaks. So when the frequency is high, lambda is less. And therefore, for a very high frequency signal, say gigahertz, if the frequency is in gigahertz, the lambda will be in centimeter only. The lambda will be in centimeter only, or in millimeter, So this is the relationship. Now here, but the wavelength of high frequency signal is very low, and it is in few meters, oblique centimeters, or millimeter. The wavelength of high frequency signal is very low. See here, if you're talking about a very high frequency signal, the wavelength lambda comes to very low. Frequency is high, but the wavelength lambda is very low. Inverse relation between frequency and lambda, means frequency and wavelength. So in this way here, this is the one idea which we have got, that frequency of a high frequency signal is having a wavelength very low, but our information signal is always a low frequency signal. but our information signal is always a low frequency signal which we cannot change. For example, a human being cannot speak. The voice frequency of the human being will be never greater than 3000 hertz, that is 3 kilohertz, that is the maximum limit. So in this way here, one logic is used. And what is the logic is used? To reduce the size of antenna, to reduce the size of antenna, because for efficient transmission, size of antenna is equal to the wavelength, that is the lambda of the information signal or that electromagnetic waves. And problem is what? The problem is information signal is always low. Therefore, size of antenna required will be in kilometer or more than kilometer. So we know one information, and that information is high frequency signal is having lambda very less. High frequency signal is having lambda very less in centimeters. So now logic, if we use, what is the logic? If we transmit low frequency signal, that is information signal. If we transmit low frequency signal, that is information signal, with the help of high frequency signal, with the help of high frequency signal, then our problem will get solved, because high frequency signals are having lambda in centimeter and the size of antenna required will be in centimeter, and that logic let us apply. So let us go to here. To solve this problem, or the size of antennas problem, to solve this problem and to reduce the size of antenna to the extent of lambda by 4, to the extent of lambda by 4 it is written now just here, or you can say to the extent of centimeters, you can say, the information signal, that is a low frequency signal, is transmitted with the help of electromagnetic waves of high frequency signal, is transmitted with the help of electromagnetic waves of high frequency signal, and therefore that high frequency signal will call as a carrier wave. That high frequency signal will call as a carrier wave, because our low frequency information signal we will transmit or we will carry, with the help of high frequency signal. So in this way, if we do this, then our size of antenna will come in centimeter. And this process of transmitting, the electromagnetic waves of low frequency signal, that is information signal, with the help of high frequency signal, to which we will call as a carrier signal, and this process is called as process of modulation. So you might have been understood now why modulation is must. So in short, I will tell you, the modulation is must because the effective transmission of information is done if and only if the size of antenna is equal to the wavelength lambda of an information signal of an electromagnetic waves, and information signal is always low frequency signal. Therefore, wavelength of low frequency signal is very high in kilometers and size of antenna required goes in kilometer. To solve this problem, we have used one logic, and that logic is, we know that a very high frequency signal are having a lambda in centimeter, that is wavelength in centimeter. Therefore, we will transmit the low frequency signal, which is our information signal, with the help of high frequency signal, and therefore we will call high frequency signal as a carrier wave. And this process of transmitting the electromagnetic waves of low frequency signal with the help of high frequency signal is called as modulation. And because of this modulation process, our size of antenna or length of antenna comes in centimeter. And this is the reason why the modulation is required. Now we'll take one example. Suppose if I use carrier signal. The carrier signal which is of very high frequency. Now frequency is measured in hertz. Hertz is the low unit. Then 100 hertz, 1000 hertz is equal to 1 kilohertz. And we have taken the example earlier of 100 kilohertz information signal, for which lambda was 3 kilometer and size of antenna was also 3 kilometer. Now we'll take one example. Suppose if we transmit the low frequency signal, that is our information signal, with the help of a very high frequency signal, say around about 300 megahertz. 300 megahertz. So megahertz is a high frequency. Megahertz is a high frequency. And for that 300 megahertz high frequency signal, we will calculate the size of antenna required, that is lambda. That is the lambda. And one more advantage in modulation is here. The size of antenna, if you do the modulation, the size of antenna is not equal to the only lambda of carrier frequency. One more advantage is what? The size of antenna is not only equal to the lambda of carrier frequency. Lambda of carrier frequency means high frequency. It becomes lambda by 4. It becomes lambda by 4 of carrier frequency due to the process of modulation. And already the high frequency signal is having a lambda in centimeter, and you are getting the advantage of lambda by 4 again because of modulation. So let us proceed for that. So here henceforth we called as a low frequency signal as an information signal, and high frequency signal as a what? Carrier signal, because this we are using to carry our information. Okay. Due to modulation, the size, that is the length of antenna, becomes equal to the lambda by 4. That is what I told you. Not only the high frequency signal are having the wavelength lambda in centimeter, but due to the process of modulation, size of antenna becomes lambda by 4, means 1/4 of wavelength of that high frequency signal, which is already in centimeter. So you will get a very good advantage. So lambda by 4 of high frequency signal, which is called carrier. The size is very, very less, approximately in few centimeter. Approximately in few centimeter. So let us consider the carrier signal f is equal to 300 megahertz. Carrier f is equal to 300 megahertz is used to carry the low frequency signal. Is used to carry a low frequency signal. Now for f is equal to 300 megahertz, the wavelength, let us calculate the wavelength. So we know the equation f is equal to c divided by lambda. F is equal to c divided by lambda, where f is equal to frequency, which we have taken 300 megahertz. C is the speed of light. We will take speed of light as a 3 into 10 raised to 8 meter per second, and lambda is the wavelength. Now here c is the velocity of the light, which will take like this here. And now what? Again here lambda is equal to mu is equal to frequency. So lambda is equal to c by f. So let us calculate the wavelength, that is this lambda, for f is equal to 300 megahertz. So substitute value. So lambda we want to calculate, that is the wavelength. I will take lambda here, equal to c is equal to 3 into 10 raised to 8 meter per second. C is equal to 3 into 8 10 raised to 8 meter per second divided by f. How much is our frequency? High frequency carrier we have taken 300 megahertz. So 300 mega means 10 raised to plus 6 hertz. Mega means 10 raised to plus 6 hertz. But here 1 by second. 1 by second is hertz. 1 by second is hertz, and meter per second it is. So here meter into hertz will be there, and this hertz will get cancelled. So only meter will remain here. So 3 into 10 raised to 8, and here 3 into 300 into 10 raised to plus 6. Now here what we'll do? 300 into 10 raised to plus 6. So 300 is 3 into 10 raised to plus 2, and this will be 6. So 10 raised to 8. So this will go as a 10 raised to minus 8. So what will remain? 3 divided by 3, and therefore lambda will come 1 meter. Lambda will come 1 meter, and lambda 1 meter. 1 meter means how much? 100 centimeter is equal to 1 meter. 100 centimeter is equal to 1 meter, and size of antenna is not only lambda. Because of modulation it becomes lambda by 4, means size of antenna is 25 centimeter, and this is the drastic reduce in the size of antenna from 3 kilometer to 25 centimeter because of modulation. And that is to only the signal of 300 megahertz. 300 megahertz. If you take to 3000 megahertz, 3000 megahertz, I think so you can understand that here it will become very, very less. It will become very, very less. And this is the size, that is the length of antenna required when carrier signal of f is equal to 300 megahertz, that is high frequency signal, is used to carry the information signal, to carry the information signal, which is our low frequency signal, because all information signals are available in low frequency only. So in this way, the first advantage of what modulation is what's here. Number one, in this way, the first advantage of modulation is size, that is the length of antenna reduces, becomes very small. And in mobile communication, carrier signal, and in mobile communication, carrier signal of 300 megahertz of 300 megahertz is also used. Therefore, the size of antenna in mobile is in centimeter, and it is inbuilt. You see the now mobiles, you don't find the antenna outside, it is inbuilt. But in mobile, there is a radio station, FM radio station, so you can go to the FM radio station and you can listen. Now, but to listen the tune, listen means to tune the radio station. Tuning is done, tuning with that radio frequency. So, but to listen FM radio station, headphone is required, headphone is must. So here, why headphone is required? Because the frequency of carrier signal in frequency modulation, FM means frequency modulation. All of you know that Radio Mirchi and all that things in Pune, you can listen this thing. They are in from 98 megahertz to 108 megahertz. 98 megahertz to 108 megahertz. So what is this 98 megahertz, 108 megahertz, 99.9 megahertz? This is the carrier frequency. This is the carrier frequency with which the voice signal of that jockey is communicated to you, and FM is using roughly we say 100 megahertz. So for 100 megahertz the size of antenna, will be in few feet, 1 feet or 1.5 feet, like that. And therefore, okay, and the size of antenna required is little bit large, not in centimeter, it is in feet. And therefore headphone cable of 2 feet or 3 feet, start working as an antenna, or it starts acting as an antenna. Therefore FM radio stations program you can listen only with the help of headphone, because in headphone there is a metallic cable, and that cable works as an antenna. But if you want to go for a mobile communication, antenna is inbuilt inside the mobile. Inside the mobile. So first advantage which we have studied, the drastically reduce in the size of the, or that is the length of antenna. That is the first advantage of what? Modulation. Now let us go to the second. Now suppose I have to pass 4-5 information signal. I have to pass 4 to 5 information signal over one particular communication channel. And suppose I have all information signal as a voice frequency of a human being, and all of them are speaking in the same language, say Hindi only. Now to transmit the voice information of that 4 peoples, those who are speaking in the same language, on one communication channel, if I transmit it directly, then voice will get mixed. So what logic is used? We will allot separate carrier frequency. For each voice frequency, and then we'll transmit it on the communication channel. And in this way, the voice will not get mixed, because carrier is different. So here, when separate carrier frequency is used for many information signals, in that case, the mixing or interference of signal will not take place. And this is one of the advantage of what your modulation. In modulation, you can allot different carrier frequency for the information signals, number of information signals which are having a same information signal frequency. So like that. Due to high frequency carrier signal, the carrier signal is always a high frequency carrier signal. That's why we have used that, because its lambda is in centimeter. So in this way here, due to high frequency carrier signal, the strength of the signal increases. And it helps in good fidelity to the receiver. Now the strength of the signal increases. How does the strength of the signal increases? That we are going to study in the next slide. Whenever you use a high frequency signal, whenever you use a high frequency signal, you know now very well the relation between frequency and lambda is inverse. The relation between frequency and lambda is inverse, means high frequency, lambda is very less. Frequency is high, lambda is very less. So here one more logic is there, and that logic is what? When you use a very high frequency signal, the strength of the signal, the power of the signal is very large. The power of the signal is very large, that you remember, and therefore what happens? The strength of the signal is very large, and therefore what happens? When you use a very high carrier frequency, when it goes to the receiver, the fidelity will be increased, means feeding the information to the radio receiver, feeding the information to the radio receiver, that fidelity will increase. Okay. Now last advantage number 4, due to high frequency carrier signal, noise is reduced. Noise is reduced because high frequency. So high frequency signal is also called short wave. Short wave it is called. Short wave means wavelength is short. Short wave means wavelength is short. So high frequency signal are having, yes, high energy. So high frequency signals are having very high energy, and it catches very less noise. So that is one more advantage of what? Modulation. In the process of modulation, what you are doing? You are carrying your low frequency information signal with the help of high frequency signal, to which you are called as a carrier, because it is carrying your low frequency information signal, and the strength of that signal is very high. It is having a high energy, therefore it catches very less noise. It catches very less noise, and that is what, in another language it is said that it is less immune to noise. Immunity is more. Immunity is more. So it is less immune to noise. Now we'll take one example. The microwave is having the frequency above 1 gigahertz. So you might have been heard at least that frequency spectrum. We have studied that frequency spectrum in the lecture 1. The frequency above 1 gigahertz are called microwave, are called microwaves. And to generate the microwave, a very huge equipment is required, because microwaves means I am talking about electromagnetic waves of 1 gigahertz frequency. So you will require a very strong magnet which is having varying magnetic field. You will require a very strong oscillator, because electrical signal and magnetic signal. Electromagnetic waves is nothing but electric and magnetic. Oscillator will give you electric signal, and very strong magnet will give you magnetic signal. So variation in the magnetic field. So in this way, here let us consider the signal of 1 gigahertz and above, and that is called microwave. That is called microwave. So if you talk about 1 gigahertz signal, you calculate the lambda by using f is equal to c divided by lambda, and then you'll understand that the wavelength lambda will be very less. The wavelength lambda, because we are taking it is in 1 gigahertz. Giga means 10 raised to plus 9 hertz. So here it is very less, and it is less than 30 centimeter. It is less than 30 centimeter. But microwaves are having very high energy. Microwaves are having very high energy, and it gets penetrated through the thin metal. Microwaves gets penetrated through a thin metal, not a thick, thin, of say less than a millimeter size. It gets penetrated through a thin metal also. Therefore, it is also used in cooking application. So you might have been understood that the microwave ovens are available in the market. So microwave ovens are used for cooking the food, and people says that it is very harmful for the human being. But we'll see what is a microwave. So the microwave is having a frequency what? 1 gigahertz or above 1 gigahertz. 1 to 3 gigahertz normally it is said. The signals having a frequencies in between 1 to 3 gigahertz, it is a microwave. Now look at this chart again. Same thing. Wavelength is very large. Wavelength is very large. Means here this wavelength we called as a time. Time is large, frequency is low. Frequency is low. So in this way, when you go on increasing the frequency, the wavelength is reduced. Wavelength comes in centimeter, because wavelength is given in meter, centimeter, millimeter, and kilometer. So like that here. So in this way here, now if you look at this application, then I have given one arrow here. See this arrow. Come to this wavelength. When you come to the lower wavelength, so here lower wavelength means here means long wavelength. Sorry. So long wavelength. Wavelength is very long. Wavelength is very long. Frequency is low. You can say. So here low frequency. Wavelength is long. Frequency is low. And remember, all L comes here. All L comes here. So here energy is also low. Energy is also low. So longer the wavelength, low the frequency. LOW. Longer the wavelength, lower the frequency and lower the energy. And lower the energy of that electromagnetic wave. I am talking about energy of the electromagnetic wave. So when you generate the electromagnetic wave of low frequency, it is having low energy. It is having a low energy. And see the graph arrow. It becomes red. It means here when you go to the short SHORT to a short wavelength in millimeter or in centimeter, to a very short wavelength in millimeter or a centimeter, the frequency is very high. The frequency is very high. And when the frequency is high, the energy is high. And when the frequency is high, the energy is high. That's why microwaves, which are having the frequency in the range of 1 gigahertz to 3 gigahertz, are called as very high energy electromagnetic waves. Are called as very high energy electromagnetic waves, and that's why they are used for microwave oven, that is cooking applications. Here this is the microwave oven. So this is the this thing here. Now you know X-ray. See, X-ray comes under where? X-ray comes to the, yes, very close to the short wavelength. X-ray comes to the very close to the short wavelength. And as we studied, as you go on increasing the frequency of electromagnetic wave, as you go on increasing the frequency of electromagnetic wave, energy also increases. Energy also increases. And therefore, see, X-rays are used for what? X-rays are used for if your bone is fractured. Doctor advice, what said? Take X-ray. So X-ray can be penetrated or X-ray can be passed through the bones also. And that's why it is said that do not expose yourself to the X-ray radiations. Do not expose yourself to the X-ray radiation. Bone becomes weak. If you take a frequently X-ray of one particular, suppose a bone, that bone becomes weak. Why it becomes weak? Because X-rays are short wavelength and they are having very high energy. They are having very high energy, and in this way, above the X-ray, there are gamma rays. There are gamma rays, and below the X-ray, there are UV, ultraviolet rays. So, ultraviolet rays are also harmful for eyes, retina. It gets damage to the retina, and therefore, the whenever you are in the region of ultraviolet rays, we use sunglasses. So that is called ray banned. So which ray is banned? Ultraviolet rays are banned. So the famous goggle name is what? Ray ban. So RAY ray. Which ray? Ultraviolet rays are banned. And that's why this glass is called ray ban glass. So in this way here, we'll focus on what? Energy. As you go on increasing the frequency of electromagnetic waves, as you go on increasing the frequency of electromagnetic waves, that electromagnetic waves of high frequency is having a short wavelength in millimeter centimeter, and it is having a very high energy. So this, I think so you understood. So now, purposes of modulation. So after understanding all that four importance of the modulation, we can link one information. Now you know that a high frequency carrier signal, high frequency carrier signal is having, of course, high frequency carrier signal, I am talking about electromagnetic wave, is having very high energy, is having very high energy. So when you use a high frequency carrier signal as an electromagnetic wave, high frequency carrier electromagnetic wave, then it is having very high energy, and therefore it gets, when it gets transmitted from transmitting antenna to receiving antenna, the noise link to that is very less. The noise link to that is very less. Very less noise is link, and therefore what we will relate here, suppose this transmitter and this is receiver, we are using very high frequency electromagnetic waves. So here noise link is very less. So noise will not get linked, and therefore you can say that signal to noise ratio, you can say that signal to noise ratio will increase. Our signal strength will be more, and noise strength will be less. So SNR. So in the last lecture only, we have studied about SNR, signal to noise ratio. So that is one more advantage. So actually we have quoted in the advantage number 4 only. So this is a signal to noise ratio, will link it because noise is very less in that high frequency electromagnetic waves. Now just let us go to the what is a modulation then. So you have understood that what is a modulation? Modulation is carrying the information signal of low frequency. Modulation is carrying the information signal of frequency with the help of modulation is carrying the low information signal of low frequency with the help of high frequency signal, and that's why we called high frequency signal as a carrier, because we carry the low information signal with the help of high information signal. So here see, suppose this is your the main block. So from here what will come? Your low frequency signal, that is information signal, will come. What is information signal? Your voice. Your voice is catched by the microphone, and this voice which is catched by the microphone converts voice signal into electrical signal. So further we will amplify it, and this signal is our information signal, which is also called as baseband signal, baseband signal. So information signal, baseband signal, modulating, MODULATING, modulating signal. These are the three names, and this signal is here low frequency. This time is very large, lambda is large. Okay, so like that here, this is the signal, and what the modulation is doing? Modulation is taking one more signal, and that is called high frequency signal, and this is a see here, the time is less, time t is less. So when time t is less, frequency is high. So modulation circuit is taking the low frequency information signal and transmitting it with the help of high frequency carrier signal, and at the output of this block, it is called modulated output, and further will amplify it with the help of power amplifier, and then we'll give it to the antenna, and this antenna converts this signal into electromagnetic waves, and that electromagnetic waves will be of what? Very high frequency. That electromagnetic waves of will be very high frequency, and that's why the size of antenna will be very less. Now here this block only will replace, because here only sine wave is shown, but this sine wave of high frequency how to generate? By using oscillator, and that is very simple now. So what is a modulation? Again the same, a baseband signal, that is also called information signal, that is also called modulating signal. See here the name, MODULATING, modulating signal, baseband signal, information signal, three names. And it is a low frequency signal, time is large, is given to the modulator, and RF oscillator, radio frequency oscillator. Radio frequencies are in higher frequencies. So this RF oscillator is used, which is generating this sine wave of high frequency. You see the time very less, and this is given over here, and this is modulated signal, which is given to the RF power amplifier, radio frequency power amplifier, and then it is given to antenna. So here this output is of very high frequency electromagnetic waves after antenna, because antenna will convert that signal into electromagnetic waves. So that electromagnetic waves will propagate in free space, with the speed of light. Now finally will come, what is a demodulator? So after transmitting the information in a free space, on the receiving side there is one more antenna, and that antenna will receive that information. So this is called receiver antenna, and when after receiving that information means what? Converting electromagnetic waves into an electrical signal. So antenna plays double role. When it is in transmitting mode, it converts electrical signal into electromagnetic waves, and when it is in receiving mode, it converts electromagnetic waves into an electrical signal. and there is one RF radio frequency amplifier, because that electromagnetic waves are in the range of radio frequency which are very high. That's why the size of antenna is reduced. So in this way, this is a receiving antenna which will convert electromagnetic waves into an electrical signal, and this electrical signal is amplified by RF amplifier. And here, by doing the demodulation, here we will require one local oscillator. We'll require one local oscillator that will study in the radio receivers. So in radio receivers, local oscillator, if we use, the demodulation process will be done with very good accuracy. And demodulation means collecting back our information signal, because what we have done in modulation, we have carried our low frequency information signal with the help of high frequency signal. Therefore, when we'll take this high frequency signal, we have to separate the high frequency signal from our low frequency signal. And separating the high frequency signal and low frequency signal, and taking only the low frequency signal, which is our information signal, which is called modulating signal, that process is called demodulation. And demodulation is must, otherwise we will not get only our information signal only. And this is the topic, that name of the topic is what? Why modulation is must and demodulation is must. And thereafter, after demodulating that, we'll go to the baseband amplifier, and then we'll give it to the speaker. So this speaker now will convert that electrical signal into audio signal. The speaker now convert that electrical signal into audio signal, and range of audio frequency means the frequency in which human being can listen is 20 hertz to 20 kilohertz. So here, this is the role of whatever one more transducer, that is called loudspeaker. Okay, loudspeaker. Okay, at the receiving end we have used the microphone. And I hope this is the information about the need of modulation and demodulation, why modulation is needed or required. And with this, I will conclude today's lecture. In the next lecture, we are going to study the details about the various types of the modulation: analog modulation, digital modulation, definition of each and every modulation. So now, today you just watch this slide again and again and try to understand the importance of modulation. Not only one, the size of antenna, but noise also get reduces. Noise also get reduces because the high frequency signal is having very high energy. And I have given the example of what? X-rays. I have given the example of microwaves. So in this way here, thank you very much for watching the video.